Hello, everyone. Welcome to our channel. Today, we're diving into the world of game plugin development, and we're going to create something truly exciting, a red light violation camera plugin. We'll be using the powerful SPF framework, which, believe me, greatly simplifies the entire process. With this framework, you'll see how easily and, most importantly, quickly you can control the in-game camera, interact with game events like traffic violations, and write your own plugins that extend the functionality of your favorite game. Our plugin will automatically detect red light violations, take screenshots from a special angle, and most importantly, it will allow you to flexibly adjust the camera's position, height, distance, and field of view directly in-game through a convenient UI. So, if you've ever dreamed of creating your own modifications or just want to learn how plugin development works, stick around. Let's get started. Plugin to be called. All right, so first things first, we need to download the API and the framework itself. Let's head over to GitHub. The address is github.com/trackhandtruckdevs. I'd really recommend you take a look at the description here. Okay, so in the quick start section, we can see that the recommended way to do this is to download the plugin template and work with that. Let's go over to the releases section and yeah, you can see there's separate CAP is here, but also the plugin template. Let's grab that template. We're also going to need the framework itself. You can either build it from scratch or, just download the pre-built version. We'll just download it. Okay, now that we got everything downloaded, let's go ahead and unzip the plugin template. I'm just going to delete the archive. We don't need it anymore. Right, time to install the framework. We need to put the framework into the plugins folder inside the game directory. Let's open up the archive and read the README file. It looks like it gives us two options. Either use the installer or manually copy the files into the game folder. Let's just use the installer. It's easier. So Windows is going to say there's no developer signature. That's totally fine. Just agree to it. I'm going to choose to install it just for ATS. And you know what? I'll also select create a desktop shortcut to have easy access to the plugins directory. Okay, click next. Double check that the installer found the correct path to the game directory and install. And as you can see, the installer put the framework in the right place for us. So now we can move on to our plugin. Let's rename my plugin to what we want our plugin to be called. We'll call it SPF_Red Light Camera. And we need to rename the files as well. All right, let's open up the project. I'm going to open it in VS Code. First off, let's get Kmay configured. We'll rename the project names inside the file and check if the game path is correct. This isn't like strictly necessary, but it's super convenient to have Kmay copy the necessary files right into the game folder after building. Okay, let's keep renaming stuff. You know what, I'll probably just use find and replace to speed things up. Okay, let's build the project. And there we go. Looks like the project built successfully. Let's check if our plugin showed up in the games folder. Yep, okay, it's here. Let's fire up the game to see if the framework actually picked up our new plugin. The game is giving us a warning that something is accessing its SDK. That's a good sign. It means it sees the framework. Just click OK. Now, press the delete key to open the framework window. We can see that the framework sees our plugin, but it's not enabled yet. Let's switch it on. According to the logs, the plugin has started. I mean, yeah, it doesn't do anything yet, but this is a fully functional, working plugin where we're going to write all our logic. All right, so let's think about how the logic is going to work. When we run a red light, and, if we have fines enabled with G_police1, the telemetry SDK gives us a gameplay event called red_signal. So we'll listen for that event, and when we catch it, we need to position the camera in front of the truck to take a screenshot. We could try to move the interior camera forward and just flip it around. Or we could try to point the begin camera at the truck, but that's all a bit too simple. I think we'll just use the free camera and position it. Um, Something like that. Once the camera is in position, we'll just send the screenshot command to the console. Okay, so we've got the logic figured out. Let's start writing some code. Okay, so yeah, let's dive into the code. For now, we're just going to set up like a skeleton just to check if everything's actually working. And then, we'll fine tune all the math for the camera. So the logic, it's going to be like a state machine frame by frame. We catch the red light event. Boom, we kick off the sequence. First frame, we position the camera. Second frame, we take the screenshot. Third frame, we put everything back the way it was. Simple and reliable, right? All right, what do we need for all this? Let's take a look at our .hpp file. Okay, SPF underscore manifest underscore API.h is already there. That's good. We'll use that to define our settings later. And to actually read those settings, we'll need SPF underscore config underscore API.h. So yeah, let's uncomment that one. Next up, to catch the red underscore signal itself, we need SPF underscore telemetry underscore API.h uncomment. To move the camera around, SPF underscore camera API.h also uncomment. And for the screenshot, to send that command to the console, we need SPF underscore game console underscore API.h. Got it. That's all for the APIs for now, I think. If anything else comes up, we'll add it. What's next? All right, the pointers and plugin context. We need to uncomment SPF underscore config underscore handle, then SPF underscore telemetry underscore handle, SPF underscore game console for API, and SPF underscore camera for API. And of course, gameplay event subscription to hold on to our event subscription. Now, we need to add some state variables for our state machine. Let's put them in plugin context. Okay, bool sequence underscore active equals false. That'll be our flag to show if the sequence is currently running. Then it's sequence underscore frame underscore counter equals 0 for like counting the frames. To put the camera back, we first need to save what it was. So let's add in original camera type. And let's also save the position and orientation right away, just in case it was a free camera. So SPF underscore effector original camera pos and SPF underscore effector original camera orientation. And let's add variables for caching our settings, so we don't have to read them from the file every single time. Those will be float setting underscore distance underscore forward, float setting underscore above, and float setting underscore field underscore right. So yeah, now we need to declare the functions themselves. Let's uncomment the prototype for the event handler, void on gameplay events, and let's also add a prototype for our future function that will position the camera. We'll call it void position and orient red light camera. It'll be empty for now, but it should be declared. All right there. I think the header file is now completely ready for our skeleton. Okay, let's go. Our header file is all set. So now we're going to tackle SPF underscore red light camera CPP itself. Right now, we're just building the full skeleton of our logic, but instead of like real actions, we'll be logging everything in detail. First off, let's get into the manifest. That's the get manifest data function. We need the framework to know about our settings, right? So we'll find where out underscore manifest dot settings JSON is. It's currently nulpture, and we'll drop in our JSON with the camera parameters. Distance underscore forward, height underscore above, and field underscore view. And of course, policy that allow user config needs to be set to true, so users can actually change them. Next up, the onActivated function. This is basically the entry point for our plugin. Here, we need to get access to all the APIs. We'll take corner for API, and from there, we'll pull out pointers to config, telemetry, camera, game console, and just neatly put all of that into our global G_CTX structure, so it's always handy. Right after that, as soon as we have config handle, let's load up our settings. We'll read distance underscore forward, height underscore above, and field underscore view from the configuration, and save them into our cache variables in G_CTX so we can access them quickly. And the most important thing in onActivated, we need to subscribe to in-game events. So we'll find _ctx.coreAPI-telemetry and call register for gameplay events, passing our on-gameplay events handler function to it. That's it. Now we're hooked in and we'll be listening to the game. Now, let's create the body for our position and orient red light camera function. For now, no complex calculations. Just, to check that it's being called. Inside, we'll grab the current telemetry data, world coordinates, local ones, the truck's heading, and just output that raw data to the log. Okay, so now for the state machine in the onUpdate function. It's pretty straightforward here. If the sequence is active, G_CTX. Sequence underscore active, we increment the frame counter. In case one of our switch, we'll call our position and orient red light camera function. As we agreed, we'll just write the current coordinates to the log. In case 2, we'll log frame 2, taking screenshot. And in case 3, frame 3, restoring camera. And then we disable the sequence by setting sequence underscore active to false. Last one is on gameplay events. This function will be listening to the game. As soon as it catches the red underscore signal event, it checks if the sequence isn't already running. If it's not, it logs that we caught the signal and then kicks. Off the machine, G_CTX dot sequence underscore active equals true, and we reset the frame counter G_CTX the sequence underscore frame underscore counter to 0. Okay, so at this stage, our skeleton is all ready to go. We've subscribed to the event, implemented the state machine logic with logging, and added a placeholder function for positioning that works. Now is the perfect time to build all this, fire up the game, run a red light, and check our logs. We should see a message for the red underscore signal, and then the sequence of logs for frame 1, frame 2, and frame 3. If all that is there, it means our foundation is working perfectly, and we can move on to the most interesting part, the math. And now for the math. It sounds scary, but it's actually pretty logical if you break it down into steps. The main problem. The game gives us the truck's coordinates in world coordinates. This is one huge single map. But the free camera we want to control works in local coordinates. To avoid issues with floating point precision far from the map's origin, the game engine uses a local grid that constantly moves with the player. Our task is to correctly convert the desired world position for the camera into the local coordinates that the setFreePosition function will understand. Step 1. Calculate where the camera should be in the world. First, we grab the truck's world position from telemetry. Then, we need its direction of travel. Telemetry gives us the rotation angle, or heading. Using some simple trigonometry, sine and cosine, we convert this angle and our distance from the settings, distance underscore forward, into an offset vector along the x and z axis. We add this vector and the height underscore above, to the truck's position. And voila! We have the exact world coordinate where our camera should be. Step 2. Find the origin of the current local grid. This is the trickiest part. We can't just ask the game, where is your 0? But we can calculate it. We do 2 things. 1. We ask the camera API for the camera's current position in world coordinates. 2. We ask the same camera API for the camera's current position in local coordinates. The difference between these 2 points is the current position of the local grid's origin relative to the world origin. So, local underscore grid underscore origin equals camera underscore world underscore position, camera underscore local underscore position. Step 3. Calculate the final local position for the camera. Now that we know where we want to be in the world and where the local grid's 0 is, it's simple. To get the final local coordinate that will pass to setFreePosition, we just subtract the local grid's origin position from our target world position. Final underscore local underscore position equals target underscore world underscore position, local underscore grid underscore origin. This is the exact vector the camera needs. Step 4. Turn the camera to face the truck. It's not enough to just place the camera, we also need to make it look at the right thing. To do this, we need to calculate the yaw, left-right, and pitch, up-down angles. We already have the offset vector from the truck to the camera. To look back at the truck, we just need the opposite of that vector. Then, using the special atten2 function, It's like a smart arctangent. We convert this direction vector into the angles we need. We pass these angles to the set free orientation function, and the camera obediently turns. And that's all the magic. It sounds complicated, but in reality, it's just converting coordinates from one system to another. Okay, all right. We're ready to replace our skeleton with like fully functional working logic. Let's go through the steps. First up, the position and orient red light camera function. This is where we'll implement all the math for positioning. To use mathematical constants, like pi, we'll include cmath and define underscore, use underscore finds at the top of the file. Inside the function, the logic goes like this. First, we get the truck's data from telemetry, so we know its position and direction. Based on that and our settings, we calculate the target world position for the camera. After that, we immediately switch to the free camera by calling camera API dash switch to SPF underscore camera underscore developer underscore free. It's really important to do it at this stage. Only after switching can we get the correct data about the camera's current position using get camera world coordinates and get free position. Based on that data, we find the zero of the local grid, calculate the final local coordinates for our camera, and pass them to camera API dash set free position. Then, we rotate the camera towards the truck. We calculate the yaw and pitch angles and pass them to camera API dash set free orientation. And finally, we set the field of view from our settings using camera API dash set free FOV. Now the function is fully operational. Next, the state machine and on update. In case 1, before calling position and orient red light camera, we save the current camera type and its coordinates. This is necessary for proper restoration. After saving, we call our positioning function. In case 2, we take a screenshot. To make sure every file has a unique name, we'll build it from a few parts. The name will look something like this: red underside underscore coordinates underscore game time. For this, we'll get the truck's coordinates and the in-game time from telemetry and use them to create the command string, which will then pass to game console API dash execute command. In case 3, we restore the camera to its original state using the save data and disable the sequence by resetting the sequence underscore active flag. The on-gameplay events function remains the same. It catches the fine event we need and kicks off this whole sequence. Let's check in the game. So here's the traffic light we're going. S worked okay, great. The screenshot is taken. The camera is working. Our plugin is already functional, but let's make it beautiful and convenient. Now we add 2 things: the flash effect when shooting to hide the camera notch, and the UI for setting it up. First, the flash. The idea is simple. For a few frames, we will show a white rectangle on the entire screen, the transparency of which will quickly change, creating the illusion of a flash. Step 1. Changes in SPF underscore red light camera.hpp. We need to include the UI underscore API and add variables to plug in context for managing the flash. 1. Uncomment hashtag include SPF-API.h. This will give us access to the user interface API. 2. Add variables to plugin context. In the plugin context section, we will need a pointer to the UI API, a handle for our Flash UI window, a flag that indicates if the flash effect is active, the current transparency of the flash from 0.0 to 1.0. 3. Declare function prototypes. We will need prototypes for the new UI-related functions. These are void on register UI and void render flash window. Step 2. Changes in SPF underscore red light camera CPP. Now, let's make changes to the implementation file. 1. Declare the UI flash window in getManifestData. In the getManifestData function, in the out_manifest.ui section, we will declare our flash window. 1. Uncomment the auto and UI equals out_manifest.ui section. 2. Set UI.windowsCount equals 1. 3. Configure our window. Name equals flash window. Is visible equals false by default, and is interactive equals false so that it doesn't intercept clicks but passes them to the game. For its dimensions, POSX, POSI, size W, size H can be set to 0, since we will be drawing it across the entire screen in Render Flash window. 2. Initialize UI API in onActivated. In the onActivated function, we will need to get the pointer to the UI API from core_API and save it to g_ctx.uipi. 3. Implement onRegisterUI. This function will be called by the framework to register UI windows. Here we will 1. Check if UI_API is valid. 2. Register our render flash window. 3. Immediately after registration, save the obtained SPF__ handle. 4. Implement render flash window. This function will draw our flash. Its logic is 1. Check if g_ctx that is_flash_active. If g_ctx flash_alpha 0.0f, and if UI is valid. 2. Get the current window or screen size. UI-get viewport size and width and height. 3. Draw a white rectangle that covers the entire screen. 5. Changes in on-gameplay events, triggering the flash when the red_signal event fires and the sequence starts. 1. Set g_ctx _active equals true. 2. Make the flash window visible. g_ctx the UI API set visibility g_ctx flash__ handle true. 3. Set the initial transparency g_ctx the flash_alpha equals 0.0f. 6. Changes in onUpdate. Flash animation, we will expand our state machine to 4 frames to properly implement the flash animation, separating the actions. 1. Case 1. In this frame, as before, we save the state of the original camera, then call position and orient red light camera to position our camera for the shot. Immediately after this, we set the initial flash transparency g_ctx flash_alpha equals 0.5f. 2. Case 2. Here we take the screenshot itself. After executing the screenshot command, we set the flash brightness to maximum g_ctx flash_alpha equals 1.0f. 3. Case 3. In this frame, we return the camera to its original state, and we begin to fade out the flash, setting the transparency to g_ctx flash_alpha equals 0.7f. For case 4, this is the final frame for cleanup. Here we completely hide the flash window g_ctx the UI API set visibility g_ctx flash__ handle false. We also reset the flag g_ctx the is_flash_active equals false. And most importantly, we end the entire sequence by setting g_ctx sequence_active equals false and g_ctx sequence_frame_counter equals 0. 5. Default. The default block should also perform cleanup in case something goes wrong and the counter goes beyond case 4. It will hide the window and reset all flags, just like in case 4. 7. Export onRegisterUI. At the bottom of the file, in SPF_get plugin, we need to uncomment and assign our function. Exports -onRegisterUI equals onRegisterUI. Let's now check in the game. So the flash works, but you can still see how the camera switches. Let's expand the flash a little. I experimented, and this is how it works. Okay, so we've sorted out the flash. Now, let's make it so that all our parameters like distance, height, and field of view can be, easily adjusted right in the game through the UI. It's actually easier than it sounds because the framework does a lot of the heavy lifting for us. Step 1. Enabling the automatic settings menu in Get Manifest Data. Okay, so inside Get Manifest Data, we find policy.config policy. This is where we tell the framework that we wanted to draw a menu for us. We just set policy.userConfigurable systems count equals 1 and add the string settings to the policy.userConfigurable systems array. And that's it, yeah? After this, a settings tab for our plugin will appear in the main framework menu. Step 2. adding metadata for our settings, also in Git manifest data. So for the framework to know how to draw our settings, we need to give it some metadata. There's a section for this, out_manifest.custom settings metadata. We set out_manifest.custom settings metadata count equals 3 because, well, we have 3 settings. Then, for each setting, distance_forward, height_above, and field_view, we create a metadata block where we specify stuff like *key path, the setting name as it is in the JSON, like distance_forward, *title key, a human-readable name for the UI, *description key, a short description of what the setting does, *widget, and this is the most important part, the widget type. We use slider to get a nice, convenient slider, *widget_params, and here we specify parameters for the slider, like the minimum and maximum values, min_val, max_val. After that, the framework will automatically create 3 sliders in our plugin's settings menu. Step 3. Implementing onSetting changed in the .cpp file. So whenever the user moves a slider, the framework calls the onSetting change function. Inside it, we get the key path of the setting that was changed. We do a simple if/else if check to figure out which exact parameter changed. Read its new value using config-getFloat and update the corresponding variable in g_ctx. Step 4. The smooth live preview OK. So to let the user instantly see the effect of their changes, we call our position and orient red light camera function at the end of onSetting changed. This creates that live preview effect. However, just simply calling this function on every slider movement was causing the camera to stutter. To fix this, we optimize position and orient red light camera 1. On the first change, when you first touch a slider, the function checks that the active camera isn't SPF_camera for developer_free. It then switches the game to this camera, activating the preview mode. 2. On subsequent changes, as you keep moving the sliders, the function sees that the camera we need is already active. So it skips the switching step and just updates the camera's position, orientation, and FOV. This approach, gives us a smooth and interactive setup. The preview mode ends when you manually select another game camera, like, for example, when you go back to the cabin view. Step 5. Exporting onSetting changed, and finally, at the bottom of the SPF_redlight camera.cpp file, in the SPF_get plugin function, we just uncomment and assign our callback. Exports-onSetting changed equals onSetting changed. All right, so let's check all this in the game. I'm already loaded up. The cargo is here. Let's open our SPF menu. Yep, there it is. We'll go to Settings. Here's our SPF_redlight camera plugin. Everything's in place. And there they are. Our 3 sliders, camera distance, height above, and field of view. Awesome. Now let's test it. So, I'm in the cabin right now. Watch this. I'm starting to drag the camera distance slider. And click. Instantly, the camera immediately switched to free mode and aimed at the truck. That's exactly what we wanted. I can move it further away, bring it closer. Now the height, just as smoothly up and down. And the field of view, perfect. Everything works in real time. It's very interactive and convenient. You can set up the perfect shot. Okay, and now to exit this mode, I'll just press my interior camera key, and voila, I'm back behind the wheel. The free camera is off. Okay, now let's run a red light. The screenshot worked. Here's our screenshot, and the distance is the one we configure in the settings. And with that, our lesson is complete. We've written a working plugin from scratch. All the source files, all the code we wrote, you can find as always on our GitHub. And now, for the most interesting part. If you found this interesting and we get, let's say, a lot of likes on this video, then in the next lesson, we'll do a major expansion on this plugin. We'll add the ability to save the screenshot to any folder on your computer, not just the default one. And also, we'll add a special filter to make the photo look like it was genuinely taken by a traffic enforcement camera, with the date, time, and maybe some kind of glitch effect. So, thank you very much for watching. Be sure to subscribe to the channel so you don't miss new videos. If you have the opportunity and desire to support our work, check out our Patreon. You'll find all the links in the description below this video.